All right, welcome back to part two. Just had to take a little break because I was going a little bit mad. So we're carrying on from our question up here where we learned that the droll did 900 joules of useful work. So I'm going to write down here that the energy transferred was 900 joules. Oh, it's still laggy. I was hoping it wasn't going to be laggy because it's a fun pen. It takes 4 seconds of time for my drone to rise through a height of 20 meters. Calculate the useful power that is developed by the blades in the time of the 4 seconds. Well, I don't need height, but I have got energy, I have got time, and I have got watts. Now, if we didn't know that we could use our previous answers for the next questions, then you'd be left with time, height, and power, and that's just not going to happen. So write down that our equation is P is equal to V over T. Power is going to be equal to 900 divided by 20. And that is going to be 900 divided by 20, 45 watts. An electric heater is connected to 230 volt supply, so V is equal to 230 volts. The power supplied to the heater is 2.6 kilowatts. Calculate the current inside the heater. I don't know how many amps. Now, I don't want this in kilowatts. I'm going to multiply that by 10 to the 3 so that I can turn it into watts. Because it's asking me for current, it's not asking me for any other kind of weird, fancy little numbers. Power is equal to current multiplied by voltage. I will divide across by V, so I can have P over V is equal to I. I'm going to have my power as 2,600 watts divided by my voltage, which is 230 volts, equal to current. Pop that into my calculator. Divided by 230, and I get 11.304, 11.30. Next question. The mass of the piece of copper is 0.058 kilograms. The volume of the piece of copper is 6.5 times 10 to the minus 6 meters cubed. Calculate the density of the piece of copper. Density equals I do not know how many kilograms per meter cubed. Checking that with that, kilograms is what we have, meters cubed is what we have, so all I have to do is density equals equal to mass divided by volume. Density is equal to 0.058 over 6.5 times 10 to the minus 6. Pop that into my calculator, 0.058 A over B, 6.5 times 10 to the power y to the x minus 6, giving me an answer of 8923.07, 8923.08. But I'll just give that as 8923. You could even give it as 8,900, and I'm sure you get the mark. Whoops, don't move that. You stay there. Stay. Okay. The next question. We have a skier going down a slope. The skier travels down the slope with a constant acceleration. Good for them. The speed of the skier is measured at points P and measured at points Q. The table in figure 10 gives some data about the skier making one downhill, I'm assuming, run. Acceleration is 3.0 meters per second squared. Speed at P is 7.6. I'm going to do this, 7.6 meters per second. And I'm going to do Q, 24 meters per second. Calculate the distance from P to Q. Use an equation selected from the list of equations at the end of this paper. So we're going to have to use the equation v squared minus u squared equals 2 times a times x. Remembering that u is my initial speed, v is my final speed. I'm going to write down that v is equal to 24, u is equal to 7.6, a is equal to 3.0. Oh, I don't believe it. I've not been putting my units in. Bad, Mr. McKelvey. Meters per second squared. And the distance is, I do not know how many meters, but I'll figure that out in a second. Now, an equation like this, there's absolutely no harm in substituting first. I'm going to do that just to save on a bit of space. So it's 24 squared minus 7.6 squared is equal to 2 times 3 times x. So I'm now going to rearrange that. Actually, it doesn't save space at all, does it? 7.6 squared divided by 2 times 3 is equal to x. Because of how useful the a over b function is on my calculator, I don't like working out things line by line. So I would have done 24 squared minus 7.6 squared, just because it can mess up. So I'm going to press a over b, 24 squared minus 7.6 squared. And then I'm going to put that over 2 times 3. And then I'll get the full number. I'll get all the decimal points. I won't have to worry about rounding anything or losing out on any marks. 94.733. done something wrong here. Ah, that's okay. That's what I've done wrong. I didn't square the 7.6. And that's how I knew I was wrong. Excellent. It's not 94.733, but I was looking at it. It didn't make sense. It seemed to be a too big a number. So I looked at my working out in my calculator, and I can easily rectify that mistake, 86.37. Calculate the time taken for the skier to travel from P to Q. All right, so we're trying to find T. I do not know how many seconds that is. You could do speed equals distance over time, but unfortunately not going to work for us because he wasn't traveling at the same rate all the way. He started at 7.6 and then went up to 24. So he wasn't traveling at the same speed. So we can't use S equals D over T because speed equals distance over time requires this to be an average speed over the total distance. That's not going to work. However, what we can use is the fact that we know the acceleration is 3.0 meters per second squared. At the end velocity was 24 meters per second. At the start velocity was 7.6 meters per second as well. Acceleration is v minus u divided by t. I'm going to rearrange this equation. I'm going to multiply across by t and divide across by a simultaneously, which just looks like they're swapping sides, but that's okay because it's what they're doing. T is equal to the end velocity of 24. Take away the start velocity of 7.6 divided by the acceleration, which is 3. I'm going to pop that into my calculator. Press A over B. 24 minus 7.6. I'm going to divide that by 3, which is the acceleration. Give me an answer of 5.4667, which I'll bring down to 5.5, just because it's a nice, neat number. One decimal place in the data usually means it's good to have one decimal place in the answer. I'm really quite chuffed that I made this mistake here, because it's a good lesson. Use the A over B function in your calculator and always check your work. For even I, the great and wonderful McKelvey, can fail. I'm neither great nor wonderful, sorry. Figure 8 shows two metal rods carrying a current. A metal roller touches both rods and completes the circuit. The roller is in the magnetic field produced by a magnet. The magnetic flux density, B, is equal to 1.2 Tesla. And the current in the roller, I, is equal to 2.5 amps. The length of the roller carrying the current, L, is equal to 0.060. Calculate the force F on the roller, and I don't know how many newtons. F is equal to B times I times L. FBI, losers, is how I remember it. F is equal to 1.2 times 2.5 times 0.06. Double checking that number. Yeah, 0.06. Put that into my calculator. 1.2. There's nothing crazy, is there? It's just amps. It's Teslas. It's just wants it in newtons. Yep. 1.2 times 2.5 times 0.06. My answer, my force on the ruler is 0.18 newtons. All right, let's go to the next page. Got 6 down and about 6 to go, I believe. A radio station transmits on 97.4 megahertz. That's the frequency. To receive the waves, an aerial needs a length equal to half the wavelength of the radio waves. So I need half of sheep daddy. Oh, this is lambda. The letter lambda. It stands for wavelength. My year 9s call it sheep daddy because lamb, sheep, daddy. So I'm trying to find the wavelength so I can eventually half it. Don't know what that is. The speed of the radio wave, so the velocity is equal to 3.0 times 10 to the 8 meters per second. Excuse me, hang on. Okay, that's gone. Right, so 97.4 megahertz, I'm going to have to multiply that by 10 to the 6 because I'm going from megahertz down to hertz. So 1 megahertz is equal to 1 million hertz. So if I want to go from megahertz to hertz, I've got to multiply by 10 to the 6 to find the overall wavelength of the wave. So I'm trying to find the wavelength. V is equal to F times lambda, divide across by V. V over F is equal to lambda. I'm going to write in that my velocity, 97.4 times, it's not my velocity. My velocity, 3.0 times 10 to the 8 divided by my frequency, 97.4 times 10 to the 6 is equal to my wavelength. Pop that into my calculator, A over B, 3 times 10 y to the x power of 8 over 97.4 times 10 y to the x power of 6, giving me an answer of 3.0 0.08. Now that is for the total wavelength, but remember that we need a length equal to half the wavelength, so I shall divide that by 2. 3.08 divided by 2 is equal to, and yes, I'm doing this in my calculator, 1.54 meters. 1.54 meters is our answer. Different circuit is then set up with two resistors as shown in figure 12, 0.2 amps, 15 ohms, and 20 ohms. Calculate the potential difference across the 15 ohm resistor. Now, let's have a look at what we've got there. We've got a current of 0.2 amps. We have a resistance of 15 ohms, and it's asking us to find the velocity of I don't know how, the voltage of I don't know how many volts. Easy to do this. If I put a voltmeter up here, I'll be able to figure it out. So what I'm going to do is my equation, V is equal to I times R. My voltage is equal to 0.2 times 15. And if I multiply those together on my calculators, it gives me, not calculators, just one, 0.2 times 15. And let's give me an error, 0.2 times 15. An answer of 3. So my potential difference is equal to 3. Calculate the total power. So if we're trying to find the power, we've got to decide which equation that we want to use. So before we decide the equation that we're going to use, we have to decide the terms that we need to collect. So let's look at the numbers I've got so far. Calculate the total power dissipated when there is a current of 0.2 amps. I is equal to 0.2 amps in the two resistors. Now, for those of you who have forgotten, in a series circuit, R total is equal to R1 plus R2, ... So the amount of resistors in series, the resistors in series, you add them together to get the total resistance. So I'm going to do that down here. My R total is equal to 15 plus 20, meaning my total resistance is 35 ohms. And the power produced then, I do not know how many watts. I've got my resistance, I've got my current, so I can use my equation P is equal to Y squared times R. P is equal to 0.25 squared times my resistance, which is 35. I shall put that into my calculator, 0.2 times 0.2 squared times 35, giving me an answer of 1.4 watts. Okay then, next question. Figure 10 shows two electrical devices for heating water. Excuse me. The current in the elements of the immersion heater is 14 amps. I is equal to 40 amps. The power of the immersion heater is 130 watts. Calculate the resistance of the immersion heater. R equals I don't know ohms. Get my answer to two significant figures. All right. So it's asking me in ohms and two significant figures. I'm going to write down my equation. P is equal to Y squared times R. Divide across by I squared, P over I squared is equal to R, giving me my answer. No, well, my substitution is 130 over 14 squared is equal to R. Are you kidding? No, I'm not. And my answer is 0.66. 66 ohms. Figure 7 shows an athlete using a fitness device. The athlete stretches the spring of the device by pulling the handles apart. The spring constant of the spring is 140 newtons per meter. Right. I'm not 100% sure if this is actually going to be in your exam. I didn't think springs were. Ah, well, I'll do it anyway. Spring constant is this. The athlete does this amount of work. E is equal to 45 joules. To extend the spring, the athlete takes 0.6 seconds times 0.6 seconds to expand the spring. Calculate the useful power output. Ah, there we go. That's why it's been included. Okay. Calculate the useful power output of the athlete when stretching the spring. So I have the energy, I have the time, I'm looking for the power. It's a 2-mark question. It's asking for watts. There's nothing to do different. So I'm just going to use power is equal to energy divided by time. If this was a 4-mark question, what they might do is ask you to work out the amount of energy that has been used by my athlete, but it's not. It's nice and simple. So we'll just say 45 divided by 0.6. Power is equal to 45 divided by 0.6 seconds, giving me 75 watts. And here we go. Another one bites the dust, as they say. Next, question 21. Almost there, folks. Only loads more to go. A different water wave has a wavelength of 0.25 meters. So I should put that down as my wavelength equal 0.25 meters and a frequency of 1.5 hertz. Calculate the wave speed, the velocity in meters per second. Who knows? I don't, but we'll figure out quite soon. V is equal to F times sheep daddy. V is equal to 1.5 times 0.25. I mean, it's criminal that they're giving that as a question in a higher paper, really, isn't it? Because with enough practice, it gets so utterly very boring. The wave speed velocity is equal to 0.375, giving me my wave speed is about 38 meters per second. But I'm going to probably 0.38. It's not 38. Why did you do that? 0.38. Two decimal places there, two decimal places there, better than 0.375. Figure 23 shows an electric car connected to a battery charger. Hey, tell you what, good that, because of the price of petrol at the moment, the car has a rechargeable battery to drive its motor. The rechargeable battery provides a potential difference of voltage of 330 volts and can store up to 664 megajoules. That's so much. It takes 64 megajoules. It takes 8 hours, a time of 8 hours for the battery to receive a full charge. Assume that the charging process is 100% efficient. Calculate the total charge that flows when the battery is being charged. Okie dokie. Asking me for Q in coulombs. Well, I can do this nice and easy, can't I? I'm going to change this into joules because my units over here are not asking for megacoulombs, they're just asking for coulombs. It's asking me to find Q. Which equation links all four of those together? None. However, the equation E is equal to Q times V does link E and Q and V. I want to get E down to normal joules, so I'm going to multiply that by 10 to the power of 6. And I'm going to divide across by V, so I've got an equation that is E over V is equal to Q. Put my numbers in. 64 times 10 to the power of 6 is equal, divided by 330 is equal to Q. Pop that into my calculator. 64 times 10 to the power of 6 divided by 330 equals 1919. Right, okay. Yeah, okay. It's just one of those weird numbers. 193,939 coulombs. That is the total amount of charge. What's going on here? Okay, right. It is right, isn't it? It's just one of those weird numbers. Sometimes they give us weird numbers to test us, don't they? Everything here is right. Calculate the total charge. Yeah, I'm completely okay with that. Calculate the average charging current. Ooh, this is exciting. All right, let's find I is equal to I don't know how many amps. Now, which numbers do I now have? I have got Q as being equal to 193,939 coulombs. It does look like a weird number. Q is equal to 193,939 coulombs. I've got the time taken, which is 8 hours. I've got the energy that has been produced, 64 megajoules. I'll multiply that by 10 to the 6 to bring it down to its base unit. And I've got the voltage of 330 volts. Which equation could I use to find my total amount of current? I've got I, I've got T, I've got E, I've got V, I've got Q, I've got I, I've got T. Either way, I'm probably going to be using T. So what I'm going to do is I'm going to multiply my hours by 60 to get minutes and by 60 again to get seconds. That's the same as multiplying by 3,600 to bring 8 hours down to seconds. I'm actually just going to do that on the side so I don't mess it up. 8 times 60 is equal to 28,800 seconds. So I shall just write that down there, 28,800 seconds. So now I can use whichever equation I want. I'm going to use Q equals I times T. I'm going to divide across by T so I can have I as a subject of the equation. And then I'm going to put in my numbers. 193,939 divided by time, 28,800 will equal my current. 193,939 divided by 28,800, and I get 6.733. Yep, 6.73, and I'm going to leave it just at that, 6.73. Now, is that correct? Let's have a look. I've got this number up here, 193,939, 193,939, 193,939. Does it ask for significant figures? It does not ask for significant figures. It is holding whole numbers, though, so that might be an issue. It is not asking for anything significant figures. No, I can keep that the way it is. 193,939 over 28,800. Yes. Now, they're being cruel to us here in that they're giving us weird numbers to use, okay? Double check your work at the end of it to make sure that you haven't been fooled. Don't let the little hobbits win. All right, so we've now got a roller coaster, a death machine. I hate roller coasters and people who ride them. The mass of this roller coaster car is 580 kilograms. I'm actually going to label this diagram just in case things get confusing later on. 580 kilograms is the mass. The car gains 39,000 joules of gravitational potential energy as it climbs from P to Q. So here my potential energy will equal 39,000 joules. State the equation relating changing gravitational potential energy, mass, gravitational field strength, and change of vertical height. Oh my word. Let us hope for a question just like that in our GCSEs. Calculate the height. I'm trying to find height in meters as shown in figure 1. They're giving me gravity is equal to 10 newtons per kilogram. We know that we got an EP of 39,000 joules and that the mass of the car was equal to 580 kilograms. I'm going to write down my equation again. E is equal to m times g times delta h. And I'm going to rearrange this to make h the subject of my equation. EP over m times g is equal to h. I'm going to substitute my numbers in. 39,000 divided by the mass, which is 580, multiplied by gravity, which is 10, is equal to the height. Pop that into my equation. A over b, 39,123, divided by a over b, and then we do 580 times 10 is equal to 6.72. 6.72 is my answer. You can leave it at 6.7 if you want to, because it was lots and lots of whole numbers. A car traveling 15 meters per second comes to rest in a distance of 14 meters when the brakes are applied. Calculate the deceleration of the car. Well, acceleration, deceleration are exactly the same thing, but its initial velocity, u, equals 15 meters per second. Its end velocity, rest, equals 0 meters per second in a distance x of 14 meters when the brakes are applied. Calculate a, which is the acceleration of the car in meters per second squared. I'm going to use my equation v squared minus u squared is equal to 2 times a times x, because I've got a distance there and not a time. So my end velocity 0 squared minus 15 squared is equal to 2 times acceleration, which I do not know, multiplied by the distance, which is 14. And I'm actually going to do my rearranging now with those numbers. 2 times 14 is equal to my deceleration. I'm going to pop that into my calculator. 0 squared. I'm going to press A over B first, just so you know what I'm doing. 0 squared. And yes, we can do this in our head, but we're not going to do it in our head because we're going to double check our work because we're scientists, not mathematicians. Giving me an answer of minus 8.04. Minus 8.04. I can hold up my calculator to my working out. I can see that what I've typed in there is correct. I've included all my squareds, so I must be fine. Let's see with time. No, we'll have to stop that there now, and we'll do part 4 all as a oneer. Okay, ta-ra.